So welcome to the 2018 April APS meeting in Columbus, Ohio. This year actually in April. My name is Clifford Will of the University of Florida, and I'm program chair for the meeting. I'd first like to thank the other members of the program committee who helped put this meeting together, in particular John Wilkerson, Tao Han, Dan Holtz, and all the program chairs of the various units that put together this exciting meeting. I'd also like to thank you, the APS members, for a full program of contributed talks. Over 1,200 contributed talks have been submitted for this meeting. Robust attendance and meaningful science and exciting frontier physics continue to be a hallmark of this April meeting. In addition to today's plenary session on Feynman's legacy, we have Monday's plenary on heavy on neutrons, from nuclear security to neutron star binaries, and Tuesday's plenary featuring APS medal winner Eugene Parker and two of our Nobel Prize winners, Ray Weiss and Barry Barish, for gravitational waves. Ray will also be giving the public lecture tonight at 7 p.m. I also want to draw your attention to some sessions that you might overlook in your mad rush to find sessions in your field given by all your own friends. This slide. So just to leave your own comfort zone for a moment, you should consider session B4, Getting the Word Out, sponsored by the Forum on Early Career Scientists and the Forum on Physics and Society. I have no idea what the title means, but there's some very interesting talks in that session. There's opportunities in nuclear science industry, diverse and inclusive workplace, forum with Congressman Bill Foster on Sunday around noontime. Pick up a sandwich and go interact with our only physicist in Congress, Bill Foster. Maybe he can explain what's actually going on in Washington. Another invited session on the legacy of Feynman, women pioneers in astronomy, and progress and challenges for women physicists in Africa, Asia, and the Middle East. So consider some of these sessions, and there are more just like them, where you can learn a little bit more than just your own narrow specialty. Finally, I urge everybody to read the Code of Conduct, which you'll find as a button in your APS meeting app. There's an icon right on the bottom of the page. We hope that everybody comports his or herself in a professional and respectful manner during this meeting. So it's now my pleasure to introduce APS President Roger Falcone, who will chair the session, introduce the speakers. Thank you.
Good morning, and welcome to our first session. Before I begin, I want to especially acknowledge the generous support of the Kavli Foundation. They helped to underwrite the costs of this special symposium. Kavli Foundation has a hallmark in their programs of support for excellent science, and they are doing that today with us by sponsoring the symposium, and we're very grateful to them, and we're very honored to have their support here for the plenary session on a Feynman century. Of course, Richard Feynman was born nearly 100 years ago. His insights into physics, his unique personality, all have fascinated and driven scientists in many fields and non-scientists for decades. And we're here today to learn more about him and his contributions. Our first speaker is Joan Fineman. Very pleased that she is here, and I'm really looking forward to her talk. As I was, she was raised in New York, but spent much of her distinguished career out in California, much of it at JPL in Southern California. She has worked in a broad set of fields, including the interaction of the solar wind with the Earth's magnetosphere, and more recently in thinking about the true science drivers for climate change. And she's had a very interesting career. I hope we hear more about it today. So, Joan, I want to welcome you to the podium, and we look forward to your talk.
Okay, can everybody hear me? Is this loud enough? Well, nobody said anything, so I don't know. Okay. Is this the right height? Or somebody help me? It sounds okay? How about people in the back? Can you hear me? Okay, good. Okay. I was invited here to talk about being Feynman's curious sister. Okay. And the first slide shows me in a fencing outfit. It's also, I was just married. I don't know what, it's questionable why you take up fencing when you get first married, but we did it because we decided we needed exercise, and we lived in a very small apartment, but there was a long porch on it that was just long enough to be fencing. And so we bought the costumes and the swords, and we read a book, and that ended our fencing. Okay. Let's see, have I, where do I, this one? This one? Yes. Okay. Although I've got a PhD in physics in 1957 in solid-state physics, this is my first appearance at the American Physical Union, at the Physical Society. I worked in space science and climate change for more than 50 years and published as first author or co-author about 185 papers, give or take 20. The most fun places I worked were Lamont, Columbia University, geophysics lab, which is, and the Jet Propulsion lab of JPL. I retired last year, and shortly after I retired, when I was figuring all the nice trips we could take, I fell downstairs backwards and broke my arm very badly, and that's why I'm limping. Although I've never understood why I'm limping because my arm is broken. But that's the way it goes. This slide is of is in recognition of exceptional scientific achievement given by NASA, just to inform you that I really am a scientist. Okay. Oh, I'm sorry. Wrong way. Yeah.
Okay, next.
Yeah. Okay. This is a picture of my family of orientation. That's a technical word, meaning the family I grew up in. And this is my mother, father, me, and my brother. Let's see.
You press this one. Yes.
What am I doing? Turn.
Press, yes. Press it. Yes, okay.
Wait a minute. In high school,
Next.
woohoo, let me jump.
Next.
This is, of course, my husband.
Okay, don't worry. Joan.
This is, of course, my husband.
Okay.
Okay. in high schools, when Richard was a kid, they used to have math contests in the states or regions, and he got the reputation of being particularly good at winning. Okay, now this is this direction?
Don't do it.
Yes. Oh, but that's
Go
the
back.
wrong one.
Go backward.
Back one.
This one.
Okay. Richard, of course, was my first teacher. He had a laboratory in his room, which was an electronics laboratory, and I was hired as his lab assistant when I was a small child, like 5, and I made 4 cents a week. That was my salary. And there's a story where my mother was having a bridge game in the living room, and she got concerned, where was Richard, what was he doing? So she called me in and she said, "Joan, would you find out if Richard is okay?" And I said, okay, and I walked down the corridor in the house. I opened his door to his lab, and he was at the window with a wastebasket full of papers and fire coming out of it. So, being 6 years old, I did as I was told. I said, "Richard, are you okay?" And he, of course, answered, yes. So I went back to my mother and reported, yes, Richard was okay. And one of the things that Richard did for me was my mother ran a pretty house where everything was done on time. And so I was in bed, and my brother was allowed to come in and say, "There's an aurora on the golf course," which was a block away, "and you should see it." So he took me out on the golf course, and I saw an aurora, and I was so impressed that I worked on the aurora for many years when I grew up. Okay. Now, what kind of time do I? Okay. My brother taught me to add numbers when I was about 3 years old. He would say, "How much is 1 and 3?" And I would say, 4. And if I was right, he would reward me. And how do you reward a little girl like me, if 4 or 5 years old? Well, he let me pull his hair. And I would take a handful of hair and pull it. And he would make a terrible, terrible face, as if he was in great pain. And then I would let it go. And it wasn't until I wrote this slide that I tried it on myself and discovered that if you take a clump of hair and pull it, there's no pain. When I learned something, my mother was impressed with Richard's teaching, not my learning. My mother warned me, women's brains can't do science, which was a common belief, and so they didn't try. In fact, college education for women in the United States there were no colleges that accepted women until 1837. Women just went to high school, and that was all they were taught. In 1937, Oberlin College in Ohio was founded. And, okay. And talking about Richard, excuse me.
Yeah.
When talking about Richard's life, I just couldn't bring myself to talk about it without talking about his first love, the love of his life, Arlene, who they were engaged at maybe 18 or 19, something like that. And she was a wonderful, beautiful girl, as you can see. And the family all loved her. She taught me to play the piano. We used to go for long bicycle rides together. She used to go to cooking class with my mother. She used to paint with my father on the weekends. He was an amateur. And everybody was very happy until we all went, the family, to a hotel in New Jersey, which had a swimming pool, which in those days was pretty rare. And we noticed a growth on Arlene's neck, and she became ill. Nobody knew what was wrong with her, but she was in the hospital for months. And then Richard married her because then he would have control of her medical. Well, he married her because he loved her, but he felt he had to be married, so he got control of the medical, what doctors she saw and so on. Arlene died of tuberculosis at the age of 27, but she was the love of his life, although he had another lovely wife later on, Gwyneth, who was the mother of his children. But I can never forget Arlene. As a matter of fact, I'm wearing a ring she gave me. Okay.
No, don't
No.
touch.
Let's
Don't
see.
touch. I'll change it.
This way?
Don't touch. Just leave it.
Yeah, okay. Okay, here's a picture of my brother as a postage stamp. This is an actual picture of an actual stamp worth 37 cents. There was a group of stamps of four scientists, and Richard was one of them. At the bottom of it, there's a saying of his: "The job of a scientist is to listen carefully to nature, not to tell nature how to behave." Okay, where am I? What time is it? What time is it?
Yeah, time is fine.
Huh?
Time is fine. Go on.
Okay. Well, this slide was going to talk about times have changed for women in science. When I first made the slide, I thought that was definitely true all over. And this question mark was added just before I came. Because, okay, in 2007, the American Physical Society produced a report on gender equality, equity, and I was insulted by it. It said, constant collection and monitoring of data to charge equity progress, coupled with attention to family-friendly policies, avoidance of subtle biases in promotion and tenure processes, and support from the top leadership are needed for women to advance in academic science. This is bunk. They're not needed. And they don't exist. Here we have the number of Nobel Prizes awarded by gender in 1901 to 2017. The total number of male Nobel Prizes was 847. The number of females that got the Nobel Prize in science was 49. In the case of physics, 205 Nobel laureates exist, of which my brother is, of course, was one. And 2 of them, out of 205, were women. They were Marie Curie and Marie Gobert-Meyer. Now that, if you think that that's because the women weren't as smart, the women aren't that dumb. And I looked at the area in which I was working, which was solar terrestrial physics. And the organization for that is American Geophysical Union. And I found that in the past 10 years of when I was looking, that no women had been given the job of a session chairman, and no women had been invited to give a paper in 10 years. Now, I happen to have been elected as secretary of a section of the organization on solar terrestrial physics. And I told the organizers of sessions that no women had been asked, and they were horrified. They didn't know it. So you couldn't blame them for not asking women. They didn't know it. And as soon as they were informed, they took care of it. And since that time, there have been plenty of women who've been session chairmen and heads of the this and that and the other thing. So some of the prejudice that women see is not known by men or women because nobody looked at the numbers. Okay, is this what I want? No, where do I want to be? That was, okay, this. Well, what is this all about? If a person wants to be a scientist, it's better to be a boy. But if a person is a girl, go for it anyway. Let's see, going to college. When I started out for college, well, first of all, my father was a very intelligent man, but he was in business. And he was ill from the time I was born till when I was 18 when he died. My father told me to learn to make a living. Only men make good livings at that time. So I figured I'd better go into a man's profession. I chose physics and hoped to be some sort of an assistant. My brother urged me to work hard to be the best. Little sisters don't usually take the advice of their brothers, and I didn't, but I did okay. When I got to graduate school, I went around, you go around to the professors in the school. It was Syracuse University, what they could profess, what they could suggest as a thesis topic. And one professor suggested to me that I study cobwebs as a thesis topic. Needless to say, I was somewhat annoyed. I chose solid-state physics, absorption of light in crystals. My thesis advisor was not interested in my work, but I did get support from other instructors in the at the university. This next are things that gave me courage to continue. First of all, I wanted to know, was this true that women were not holding high office in the past? And where would I get the information? Well, I figured that the Bible would have the information because nobody made things up specifically for the Bible. I mean, everybody put in what they believed, and they all believed the same thing. And in the Bible, in the Old Testament, it says, and Deborah was a judge in Israel. It didn't say what Deborah did as a judge, but it was a high office, and she was a woman. There's also in the Jewish religion, an Orthodox Jew the men will go to the synagogue on Friday night, and when they come home, they recite a praise of virtuous woman. She seeth the vineyard and buyeth it. Not, she seeth the vineyard and tells her husband to look at it, and if he thinks it's a good idea, then he should buy it. She bought it. Okay. And that gave me courage that it was not universally. And then I learned some anthropology, and there were other cultures in which women were the primary person. And my grandmother, who was pictured here, after whom I was named, was a watchmaker and a milliner. And you can tell from her clothes she didn't do too badly. What time is it? Okay. But as an example of segregation of women, I thought this was a very nice picture of the situation. It's in France. I was working in the National Science Foundation.
I don't know where is this.
Huh?
I couldn't find that.
What?
Couldn't find that slide. Yes.
Yeah. I was working in the National Science Foundation and was invited to an American Geophysical Union committee meeting in a famous building in Washington. So I walked over there. They wanted my input. So I walked over there, and I walked in. And there was a dining room, and there was an elevator to the next floor. So I knew the conference room was on the next floor. But as I went to get into the elevator, you see this picture? That's what happened to me. Suddenly, there were 4 men around me saying, "You can't go up. You're a woman." So, since I had a role in the American Geophysical Union ruling group, I initiated a rule forbidding meetings in any segregated buildings. And that was unanimously agreed. And it was one of the things I felt good about.
Okay, move.
Whoops, wrong way.
Don't touch this. I'll touch this. You move it.
Okay.
Go to curious.
Well, I need to see it.
Yes, this one.
Let me turn one page.
You pass it already. You pass this one.
What a woman does need, in my opinion, is love of the subject, hard work, determination, bravery, and persistence. How am I doing on time?
3 minutes. You have to go.
Mm-hmm.
Go.
Okay.
Yeah, okay.
Okay, now I change the subject to a paper to tell you about, because I think it's an interesting paper, and it's probably my last paper, because at my age you don't get younger every year. This is a cave art in the south of France. The art, the 4 horses, is a photograph of what's on the wall. And if I look at those 4 horses, I see beautiful drawings expressing their intensity and strength. And to me, it's just great art. This art was put on the wall 31,000 years ago by somebody. There was no agriculture 31,000 years ago. In fact, there was no agriculture until 10,600 years ago. Why did it take 20,000 years after these beautiful paintings were made on the wall to invent agriculture? That seemed to me to be a curious observation. Then what happened? Agriculture was suddenly invented more than once in very distant areas. I listed 3 of them, but there were more. In the Levant, in the area of Israel and near that area, the first agriculture was the domestication of wheat and barley in the Levant. Rice was invented in China and Japan. Now, China and Japan at those days could not have a strong relationship with another. They had to be separate. And then corn was domesticated in the Americas, particularly in southern Mexico. Now, the next slide shows the time when this happened. In the Levant, from 11,000 to 9,500 years ago, the species that were domesticated were wheat, barley, chickpeas, flax, sheep, and goats. Now, in China, at about the same time, the domestication was rice, millet, pigs, and silkworms. In Mesoamerica, they don't know how early it started, but I think they know better than that now. Anyway, it was corn, beans, squash, and turkey. Now, these are obviously independent. You don't need a silkworm in order to make chickpeas. It didn't go from one to another. And so, how could it be that for 2,000, before it was 33,000, for 20,000 years, there was no okay. This final slide gives a history of the climate during the last 50,000 years. Now, how do you get a history of the climate for the last 50,000 years? You dig in the polar regions, deep ice cores, and you analyze the ions in them. This data is on the ion, in the upper panel is the ion the amount of the ions. And the other panels, the lower panels, are the empirical modes and the variations with frequency between 1 in 200 years and 1 in 2,000. And sodium gets into the ice by the winds that are blowing. And so this first top shows that the weather throughout the 50,000 years, which is shown, was very disturbed. And the lower four shows what the frequency of the disturbance was. And you will note that 11,000 years ago in the top one, and in all of them, 11,000 years ago, it stopped varying. So that allowed agriculture to appear. Okay. The problem now is, why did climate become stable after 11,000 years ago? And is climate becoming unstable again it certainly seems to have changed. And what can we do about it?
Can Richard last words?
Who knows? But I would like to give you Richard's last message to the world. He was always giving messages to the world as he saw it. He was dying of cancer. He was in a coma, and he began to move, and he went like this, which says, nothing's up my sleeve, and I'm not holding anything. And then he said, this dying is boring. I wouldn't want to do it again. So Richard died with a sense of humor and telling the truth, as usual. So that's,
Thank you.
so thank you. Are there any questions?
What's your step? Your step.
Oh, good you mentioned it. I'd forgotten.
Joan, thank you very, very much. I think if any of you have questions, Joan might be here at the end, and you could come down and speak with her. But that was wonderful. Thank you. Our next speaker in the symposium is Kris Munroe. Kris was educated at MIT and University of Colorado. He's worked with many, many distinguished groups around the world. He has a career that spans from NIST, University of Michigan, now at University of Maryland, and the Joint Quantum Institute there. He is an international expert in atomic, molecular, and optical physics, and I think the topic of his talk today, more toward quantum information science. So, Kris, I want to welcome you to the stage.
Okay, thanks. Okay, thank you, Roger, for the kind introduction, and it is indeed my pleasure to speak at this this wonderful celebration of Feynman's life and times. And it, as most of us know, certainly in my generation, we are aware of Feynman's influence, not just in the foundations of quantum electrodynamics, as we'll hear in our next talk, but almost everything. He seemed to be a tinkerer, and he was very interested in devices, miniaturizing things. And as I learned later in life, he was very interested in computing and what it means to compute. And as a physicist, I think he was able to appreciate that computing is physical, and if you want to store information, process information, you have to dive down into the fundamental physics of the device that is storing or processing that information. Now, when we look at the history of computing, as an experimentalist, I like to think of the devices that were built, and in the 19th century, Charles Babbage is known to have built a mechanical type computer, and it's unfortunate that at the time there was no underlying theory of what computing meant. And I think it's sort of a shame that at that time, electrical relays existed, and I don't think it was realized that they could also store information and compute at the time. Maybe it was realized, but I think the reason Babbage's machine didn't take off was because it wasn't appreciated how universal computing can be. And remarkably, that took another century to be determined by folks from Alan Turing, Claude Shannon, and others. As you probably know, Turing invented the idea of a universal computing machine. Even though it wasn't a practical device necessarily, it involved tapes and heads that would change bits and so forth. And I think on the more theoretical side, Claude Shannon from AT&T Bell Labs back then, he showed there's a unifying theory of computation involving bits. And wherever you store your bits, it doesn't matter. You can use that to compute. And he, in fact, as physicists, we all know this expression as the expression of the entropy of a single bit. And if you have an alphabet of letters with probabilities p sub I, this is sort of the entropy of a given letter from that alphabet. And the simplest example of that is, say, an evenly weighted coin, 50-50 odds, and when you plug it through this equation here, the entropy of an evenly weighted coin is log 2. Each piece of heads is 1/2, piece of tails is 1/2. So you add the two terms, 1/2 log 1/2, twice that is log 2. So we have the concept of entropy coming from an information theory point of view. And I'm going to return to that topic in a moment. And to me, as weird as this was, we're all students of thermodynamics and statistical mechanics. There is indeed a close link between the thermodynamic entropy we know. And for me, this was only elucidated in the works of Feynman in some of his lectures on computation. But Shannon's contribution here, I think, was much more than theoretical. It allowed engineers and scientists of all types to look for bits in nature and use them as computers. And of course, at the time of Shannon's theory in the 40s, the state-of-the-art computer was based on vacuum tubes. Vacuum tube gates, and these were nonlinear devices that allowed gates to process information in a universal way. And this is a picture. You've seen pictures of the first American digital computer. This one called ENIAC at the University of Pennsylvania. It had some 5,000 vacuum tubes that were quite unreliable. And in fact, some of these women, some of their jobs were to actually change those vacuum tubes because they broke so often. But the point here is that the vacuum tube was the only technology, really. It was the best technology at the time. And based on these triode tubes, it's sort of archaic now to think of it in those terms. And that's because shortly after ENIAC was unveiled, there was this wonderful picture we all know of the first solid-state transistor. This is work of Bardeen, Brattain, and Shockley. Of course, it earned their Nobel Prize. And this is a chunk of germanium on the bottom here, and there's a gold contact on this electrode. And this doesn't look like an electronic circuit, really. It looks like a physics garage experiment. And in fact, these devices were not very reliable either. In fact, you would say it was sort of a decline from having vacuum tubes. But I think because this system was solid state and not a vacuum tube, at the time, Feynman, among others, was inspired by this because he, I think, saw that it could be miniaturized. And so in my title, I talk about Feynman's opportunity. What do I mean by that? Well, the opportunity of this solid-state transistor gave us, indirectly, it gave us Moore's law. And as you know, Moore's law expresses the continual shrinking of transistors and their increase in performance throughout the decades. And this is a plot, you've all seen different versions of this plot, I'm sure. Over the last several decades, we've seen exponential growth in the capacity of computer processors. And here we have, as a function of the year, we have a log plot of the number of transistors on a single processor at the time. And the blue dots are the Intel chips that we find in PCs, and the red ones are Motorola chips in the early days that were found in Macs and Apples. Obviously, they're using the same technologies, just different packages. And so this indeed was made possible because we learned through the course of several decades how to make transistors reliable, how to make them really small. And because the transistors are based on solid-state materials, there's no reason to not keep shrinking, and that's happening right now. The problem with Moore's law, or at least one perceived problem, I don't really know a way out of this conventional Moore's law, is that if we continue along this exponential path, sooner or later these transistors are going to be so small that they will approach individual atomic scale. And that's a problem if you want to keep shrinking things. We have to think of different ways to improve the performance and capacity of computers. And I think Feynman, back in the 40s and 50s, none of us could have anticipated this explosive growth, but this is the opportunity. And he had, many of you know, he gave a talk like I'm giving now at an APS meeting a long time ago, 1959, and it's a wonderful lecture called "There's Plenty of Room at the Bottom." And here he was again tinkering with the idea of information and making computers really small. And my favorite line in this 3 or 4 page essay, it's been typewritten and it's available online. He talks about making transistors down to individual atomic size. And this is, I mean, so far ahead of its time, 50, 60 years ahead of its time, where we're now seeing this. And he leaves this zinger in there. He doesn't really know what it means, but he says, when we get there, it gives us completely new opportunities for design. Why? Well, because when you make things really small and isolated and individual atomic scale, we know that the laws of physics are completely different than the classical laws of physics behind classical electronics. Now, you can argue that a solid-state transistor actually involves tunneling, and that's quantum and so forth, and it is indeed true, but I, for one, didn't learn electronics and transistors from quantum mechanics. We learn it sort of from a high level. It's a 3-terminal device, and it works this way and that way. You don't really need the fundamental tenets of quantum mechanics to understand that. But if you want to understand atomic structure and nuclear structure, things that involve fundamental particles, you have no choice but use quantum mechanics. And so this is the opportunity that Feynman put out in 1959. And I guess as we're learning over the last few decades, it took 40 years or so for this opportunity to be realized. And I'll return to that in a moment. I want to take a slight detour. Feynman's work throughout the decades has weaved its way through the field of quantum information and quantum computing in many different ways, at least 3 different ways. And so this is one, and I'll return to this, basically the advent of quantum computing being his opportunity. But there's another aspect that happened in between. And so I'm going to dwell on this for a moment because it's quite interesting how thinking about classical computing and fundamental issues in classical computing led us to quantum computers. And Feynman was instrumental in that, even though we didn't know what they were useful for at the time. And you could argue we still don't. Feynman, at this meeting at MIT in 1981, a lot of computer scientists here, I think this was a meeting that was hosted by IBM. And I point out Feynman with the yellow dot there, but another important actor at this meeting is Rolf Landauer. He's sitting down right here. Rolf Landauer was a scientist at IBM, Watson Lab in Yorktown. And Landauer, believe it or not, had pretty much figured out in the 70s the solution to Maxwell's demon, the thermodynamic puzzle that seems to allow us to make refrigerators without work and so forth. And the reason he was thinking about Maxwell's demon had to do with information. It had to do with the dissipation in computer devices. So we all know that classical computers are based on gates. universal families of gates. It almost doesn't matter what gate family you choose, an OR gate, an AND gate, a NAND gate, and so forth. If you can apply those types of gates on any sets of bits in your system, you can do a universal computation. This is related to the Turing machine I showed earlier. If you can manipulate bits in that way, have them interact through these multi-bit gates, you can do computation. Well, in practice, to do a NAND gate, for instance, requires that we hook up a couple of transistors with a resistor and a power supply, and we may have a 5 volts as a logical 1 and 0 volts as a logical 0. We're running currents through wires and resistors, and there's dissipation. When we run these gates and we switch, we basically operate Turing's tape and flip bits around. There's a lot of dissipation involved, and at IBM, among other places, it was very important to understand what that dissipation is. And especially as computers get smaller and smaller, they basically become power factories, and it's very important to dissipate that power. It leads to faster computation and so forth. Well, in the 70s, the state-of-the-art computer, of the amount of power it dissipated, I can't say how many nines, maybe 24 nines, 99.999924 times percent of the power dissipated was just usual ohmic loss in these resistors. But there was a tiny bit left over. And this is very fundamental, and Landauer was interested in this tiny bit of fundamental dissipation. And it has to do with information. Now, the 2-bit gates that we use, like the NAND gate, they have 2 inputs and 1 output. Any Boolean logical function of 2 inputs, you usually have 2 inputs and 1 output. So you're throwing away information. And this is the fundamental dissipation that Landauer was interested in. And again, at the time, that dissipation was a 10 to the minus 24 of the total dissipation in the computer, so it was a very academic thing to think about that. Why would anybody care at that level? Well, that's why we do science. You don't really have to have a reason to do it. But in this particular case, I would say studying that process probably fast-forwarded our appreciation of what quantum computing is and could do. So at this meeting, Landauer was going through his ideas on how when you lose entropy by throwing away information, there's a fundamental amount of dissipation you've lost there. And some other folks in the audience here, Charlie Bennett from IBM, Toffoli from BU, Paul Benioff from, now he's at Argonne National Labs. They were all sort of thinking, well, can't we make a reversible gate, like an AND gate? Can't we somehow rewire it so that we don't have to lose entropy? We don't have to worry about this 10 to the minus 24 inefficiency. They were all thinking how hard it is to do that. They had billiard ball models, analog models of how you do these. And analog computers are not very stable, very hard to maintain their performance. And so at this meeting, Feynman, scribbling in the back of the room, from what I'm told, he stood up and said, well, I know a reversible way to make a gate. It stems from a reversible theory, and that is quantum physics. Quantum mechanics is inherently reversible, at least the part where you don't measure, the coherent part, the Schrodinger equation. He said, well, let's make a quantum gate. So Paul Benioff was in the audience, and he began scribbling really heavy about universal quantum logic gate families and so forth. So this is 1981. We still didn't know what a quantum computer could be used for, but at least we knew that it could be built out of quantum gates, and we could not have this 10 to the minus 24 inefficiency. So again, it sounds kind of academic. And so this, when I was a student, I bought this book, The Feynman Lectures on Computation. Now, most of us know Feynman's lectures from his three-volume set of Physics 101 and 102 and 103 and 104 from Caltech. But this one's a wonderful read. Again, it sort of bounces around in many different areas. But Feynman made the connection, at least for me, between information entropy and thermodynamic entropy. And his arguments were a little bizarre. They had to do with storing data in an ideal gas of exactly one molecule or one atom. And so an ideal gas usually means that you have a huge number and you have pressure and so forth. Well, if you have one molecule in a box of a well-defined volume, he posited that you could store a single bit of information by indicating whether this particle is on the left-hand partition or the right-hand partition. So there's your bit, and again, we're seeing in action that bits are physical. Computing is physical, and you have to look at the physics of what you're doing here. Well, if you run a gate with this type of a bit, and you throw away bits, it's sort of like erasing bits. And if the background is at a temperature T, we can apply some very simple thermodynamics. And to initialize, to zero these bits, you can do this by having a piston. Wherever the molecule is, we can have a piston, push it over to the left, and make sure we have a 0. That's called an erase operation, an erasure. And it takes some amount of work to do that. If we have this single molecule at temperature T, it's bouncing against the piston. It takes some work to do that, and an associated amount of energy, which is kT log 2, if it's an isothermal process. Simple thermodynamics, kT log 2. Well, the entropy at constant temperature there is k log 2. And apart from the constant Boltzmann's constant here, this is exactly the Shannon entropy. And to me, this was, even though it's bizarre to think of a single molecule ideal gas, to me, this connected all kinds of wires in my head. Being a student of thermodynamics and just learning information theory and seeing the same type of expression. They are the same. And that's a little controversial, I gather, but I'm okay with this. I think making that connection is very important. So at this meeting then, I would say was the birth of the idea of using quantum gates, but we still didn't know what they were good for. And this took another decade or so, and it's a very subtle story, and I want to tell you a little bit about quantum computing and what I consider to be Feynman's grand opportunity that he spelled out in 1959. Now, a quantum computer involves quantum bits instead of classical bits, and of course, in quantum mechanics, we are allowed to store superpositions of 0 and 1. Well, I like to think of, when you put a lot of bits together, quantum bits together, there's sort of a good news, a bad news, and then a final piece of good news, which is the opportunity. Well, the first piece of good news, if you imagine this block diagram of our quantum computer, we can do massively parallel computation. If we have n bits, there are 2 to the n configurations of those bits, and they can be stored in superposition, right, with any amount of weighting. This is just 3 bits. With 3 bits, there are 8 amplitudes of those 8 binary numbers. And of course, these amplitudes follow a wave equation. It's very complicated, but it's reversible and it's unitary, and we can apply quantum gates to manipulate this system. And it seems like we're doing things in parallel. If you want to compute a one-to-one function, you get to compute them all with one turn of the crank. Now, 3 is pretty trivial. 8's not a very big number, but if you make this number medium size, say 300 atoms or electrons or photons, and you can somehow control them all, well, you have to deal with a space of 2 to the 300 configurations, 2 to the 300 possibilities. And of course, 2 to the 300 is huge. It's more than the number of particles in the universe. So therefore, you could argue that a classical computer will never be able to approach this amount of, I have to be careful here, storage capacity. It's not computing power. I put it in quotes because there's some bad news coming. So if you have 2 to the 300 pieces of information running around this machine, that's really interesting, but it's not useful until you look at it. And of course, now the irreversible part of quantum mechanics rears its ugly head, and when you measure a quantum superposition, of course, it pops into a random result. And so now we think of this as very negative. It's almost like noise. It is. We can think of it as noise, if you want. And while you did all these parallel computations, you only got one answer. And even worse, you don't know what answer you got because it's random, right? So I'm pretty sure that this makes quantum computers no more powerful than classical computers, probably even less so, for one-to-one functions. Well, there's a final piece of good news, and this took another decade after that MIT meeting, and it's largely owed to David Deutsch from the University of Oxford. And again, an example of somebody who knew quantum mechanics and information theory and put them together. Now, Deutsch recognized that, well, these amplitudes, these 2 to the 300 amplitudes, they follow a wave equation, and they can interfere. They can interfere constructively, destructively, and the very abstract idea here is that we can process these superpositions. It's very hard to draw what's going on here, but these red dots in that rightmost figure there, those are supposed to denote gates, interferences. And they're only, I guess I've drawn them to be only binary, but there's a whole rich family of operations you can do there. But there exist situations where almost all of those amplitudes destructively interfere. And only one or a few, not 2 to the 300, but a few, maybe 300 of them remain. And then when you measure, it's not nearly as random as it started. So we're looking for problems. I mean, I'm not pointing to any particular problems that can be cast in this way. It's not obvious there are any. Turns out there are. I'll talk very briefly about that. But these quantum gates that Paul Benioff started thinking about also with Feynman may allow us to process quantum states to give an answer that could be interesting. Think about it. With 2 to the 300 inputs, we could get an answer that depends on all inputs. There could be an algorithm where this is a global property of all those inputs. And that means that a classical computer would never, ever be able to deal with that problem. I don't care how far you take Moore's law. If it's classical physics, there's not enough stuff in the universe. Well, unless we want to break apart atoms inside our computer. I suppose you could always leave that open. So these quantum gates give rise to a property called entanglement. And again, to this crowd, I think you've heard of the term, and it was first introduced a long time ago as actually a supposed counterexample to the reasonableness of quantum mechanics. Einstein introduced so-called entangled states that seem to defy reality. They seem to violate all kinds of laws of physics. And using the language of quantum information and quantum bits, we can write an entangled state. This is one of the simplest forms of just 2 qubits, quantum bits, that are in this funny superposition where when you measure this superposition, there's perfect correlations. They're either both 0 or both 1 upon measurement, but if you look at them individually, they're perfectly random. Okay? That's a property of quantum entanglement. So what type of algorithms can evoke this entanglement to actually result in useful things? And I would say the big killer app occurred in 1994 when Peter Shor at AT&T Bell Labs, he's now at MIT, he showed that a quantum computer, if you could build one, would be able to factor numbers in polynomial time with the size of the input. Classically, the only known algorithms to do this are exponential with the number of bits representing the number you want to factor. And as you probably know, the inability to factor big numbers is the reason data is secure on the internet and everywhere else. So factoring is a very important problem for decryption. And so in 1994, Peter Shor and the idea of quantum computing shook the NSA to its core, basically, because this called into question the security of data. Now, the sort of good news, we're not alarmed by this now because it's been 20 plus years, and we still can't factor an interesting number. Quantum computers obviously are really fragile. The qubits have to be isolated. You have to be able to store superpositions without looking. And to factor an interesting number, maybe one with 10,000 bits, may require millions of qubits, because one thing I didn't talk about is error correction, which is an extension of classical error correction. You can do this with quantum systems. And it may require millions of quantum bits and billions of operations. And we're so far away from that even now that nobody is really worried about the factoring devices at this point. But you never know. 30 or 40 years from now, it's very hard to predict, especially in technology and in computers. Another application, I won't talk about it much, it's called Grover's algorithm, and it allowed for quantum searches to proceed quadratically faster than any classical counterpart. But the first one is exponential gains, and that's the big deal. Now, the last area I would say I want to cover where Feynman had an incredible influence in the field was not on factoring or quantum search. In fact, it was before 1994 when this field really took off. His idea was, well, if we can do quantum computing with quantum gates, then that's a very good place to think about simulating or modeling real quantum mechanics, like QCD, for instance. QCD, lattice gauge theory, is a very hard theory to do. It's intense computationally. It's a quantum problem. It's a many-body problem. We see problems like that in all of physics, from high energy down to condensed matter. And so Feynman had this idea of quantum simulation. And nowadays, we're starting to use devices to do very small quantum simulations. and they may even lead to new materials in the future. And again, I don't have time to get into these in too much detail, but a quantum simulation is something that maybe in the near term we can learn a little bit about how certain quantum models perform. So I want to close. I'm very low on time, and I skipped through a bunch of things here, but it's an interesting time right now in the field. When you hear this at a plenary talk, you should watch your wallets and so forth. But in quantum computing right now, there are two technologies that are really sticking out. There are many other technologies that are still very researchy, but these two technologies are starting to be built into systems. And although I'm a physicist, I'm becoming knowledgeable with the idea of systems engineering. And I think many of you, if you work at big accelerator facilities and so forth, you understand that as well. These big systems are, each individual part is not so hard, but the complexity of the overall system is ridiculous. And we're starting to build systems out of both superconducting qubits and individual atom qubits. And these are wildly different technologies, and they're complementary in many forms. And they have different challenges and so forth. Superconducting systems are made on a chip, even though you have to get them very cold. They're printed on a chip, and it's leveraged by conventional lithographic techniques. In my world, I work with individual atoms. They're in a, I hesitate to say this, they're in a vacuum tube, so we're sort of back to vacuum tubes. That's a real bummer. But the system is at room temperature. The system is at room temperature. But because the atoms are in a vacuum tube, they can be laser cooled, so they're very cold, but it's not like we need a refrigerator for that. The vacuum prevents any thermal contact with the walls. And we use lasers and optics to control these atoms and wire them together. Now, what's really interesting in the last few years is there have been huge outsized investments in these technologies, especially superconductors, and especially from industry, the behemoths. You can see them right there, Google, IBM. So people think that a quantum computer, if one is built, we may find new applications for them. It's still a rather speculative field, but the fact is companies are making bets here, and it's sort of a big deal. And I'm going to actually, since I'm very low on time, I'm going to skip through and project another one of our favorite quotes of Feynman. And this one is on the topic of quantum simulation. And he realized more than anybody that quantum simulations are hard if you want to model how particles interact in many different contexts. These Feynman diagrams are, as we'll hear in the next talk, I mean, they get pretty complicated pretty fast. Well, he had the idea that, well, a quantum computer could be used to simulate a quantum system. And if you're going to simulate a quantum system, you better be able to have a quantum system do that. A regular computer is just not necessarily going to be good enough. And I think what a lot of these companies are thinking, and the promise of quantum computing is not necessarily factoring, although that's always there, or search. It has to do with a more vague area of optimization. The idea that, remember I said early on, quantum computers are good at finding global properties of lots of inputs. Well, optimization is exactly that. If you have a very complex system that has many local minima and maxima, to find the global minimum is usually a hard problem. You have to sample, the entire landscape to do that, and that's exponentially expensive. The traveling salesman problems. We don't think a quantum computer can solve the traveling salesman problem, but it might be able to do it better than a classical computer could in terms of an approximation. So the traveling salesman problem is an easy problem to state, but it's very hard because there's so many configurations. And it's these problems that many in the community are starting to think about. And so I guess I'll conclude. I saw Roger and Cliff putting up some slides on some opportunities in policy. Well, because I'm in the Beltway, I happen to work in the Beltway, I sort of got roped into very high-level dealings with Congress on the potential for a national quantum initiative. And this is motivated in part by the potential application of quantum computing, but also that there's a workforce issue. And I like to say that at companies, they don't necessarily have the cast of quantum engineers yet. These are sort of like, I'm going back to 1950, VLSI, the scaling down of transistors that led to Moore's law, took a new generation of engineers that in semiconductor fab, knowing that you needed things to be clean and so forth. The engineers that made VLSI possible and Moore's Law possible were not vacuum tube engineers in general. And you think about that today, the engineers that make computers, they might know a little bit about quantum mechanics, but they're not steeped in it, like you in this room. We take the rules for granted, quantum physics rules for granted. Engineers in the future need to do that. At the universities, we're great in quantum mechanics. We love it, we teach it, all our students know it, but we don't build anything. You can't build anything at a university. Hate to think about that, but we can't build something. An autonomous computer that somebody uses can't be built at a university. So there's sort of a workforce gap, and the National Quantum Initiative that is being promoted, in fact, Congress right now is studying this, and Roger knows all about this through the APS as well, that there needs to be a concerted effort between our civilian agencies, DoD, and the intelligence community to have a very vibrant and unified approach in quantum computing. It's happening throughout the world, especially Europe and China, and I'm happy to field any questions you have on this NQI. And when you meet with Congressman Foster, he knows all about this, of course. You should ask him some questions as well. So with that, I think I ran out of time. I thank you for your attention and take any questions.
You'll be around very much, a few minutes at the end if people have questions, especially about National Quantum Initiative. I think it's a very exciting idea, and I wish you great luck with that. But thank you again. Our final speaker in the session is Roxanne Springer. She is a professor of physics at Duke University, very active in and a fellow of the American Physical Society. We're very proud of recognizing her for that. I understand her field. I don't understand her field. I understand that she studies weak interactions, quantum chromodynamics, QCD, relevant to both nuclear physics, particle physics, and very excited to hear from her today. So welcome, Roxanne.
Thank you. The 100th anniversary of Richard Feynman's birth is an opportunity for us to honor his scientific achievements, and it's also a time where we can reflect on how we have built on his foundations to deepen our understanding of nuclear and particle phenomena. What I want to do today is to choose just a few of Feynman's methods and ideas and track their impact on present results. That includes the path integral formalization, the renormalization of field theories, the use of the parton concept, and of course, Feynman diagrams. In the process of generating his new ideas, and you've seen some of this from the previous two speakers, Feynman modeled what we could call his scientific method. And that includes questioning the accepted wisdom in physics and making sure that he understood a problem by working it out on his own, in his own way. He was somewhat famous for not wanting to even see how anybody else had solved a problem before he had the chance to look at it on his own. And he was also famous for working out pages and pages of a long calculation and then pausing and stepping back and saying, I wonder why this was obvious. And this illustrates two important parts about Feynman's scientific method. It's not only important to understand something in your own way, but to understand it in as many different points of view as possible. Feynman also communicated the joy that comes from the process of meeting physics challenges and solving problems. Today, we apply these methods to quantum field theory, and two powerful tools that he anticipated is lattice gauge theory, something Kris Munroe alluded to a moment ago, and also effective field theory. So I want to describe what those are and why they're so impactful. Also, what we could call Feynman's scientific method, the way he did science, is actually what we call today a growth mindset. And this is actually a recipe for how to discover new physics and, critically, how to enable a student of physics to thrive. Quantum chromodynamics is a perfect forum to learn about and appreciate Feynman's impact. And that's not only because it's involved in almost all of particle and nuclear phenomenon, even if you're looking at creating new particles beyond the standard model physics, it's still the case that you're going to have to wade through QCD in order to figure out what it is that you're measuring. So one thing that makes QCD so dramatic is that it's kind of surprising that we're all made up of protons and neutrons, and yet we have no idea how they get their mass. The Higgs boson gives mass to quarks, and as you can see, the amount of the mass of the proton that comes from the individual quarks, the two up quarks and the down quarks, is a very, very small percentage of the total mass that it has. That comes from QCD. Feynman diagrams, path integral methods, and renormalization all turn out to be critical to our ability to make predictions from QCD. And of course, any beyond the standard model theory has got to agree with QCD predictions when we finally discover it. Ultimately, our goal is to be able to calculate from the quark-gluon language of the QCD Lagrangian to make hadronic bound states and ultimately even get to heavy nuclei, the nuclei that make life possible. Let's first look at what Feynman knew back in when the first data from SLAC was coming up on inelastic electron-proton scattering. What he realized is that he could encode what measurements were being made by considering hard point-like things in a proton. So at that time, what we knew is that there was this hard thing in a proton, and that was not really obvious. Recall that when people first wondered what an atom was made of, when people first wondered what a nucleus was made of, it wasn't at all obvious whether charges were uniformly distributed or whether there were point-like objects inside. What we now know is that the proton is a very complicated picture of quarks, anti-quarks, the valence quarks, the C-quarks, quark anti-quark pairs and gluons. And what I want to put in your mind is that this parton picture is actually what we would now call an effective theory, in that it encoded what was known at the time in the degrees of freedom that were thought to be important. Now we know that if we go in with higher and higher energy and look at a proton, we actually see more and more hard things, which are the quarks and gluons of today. So how do you make a proton from quarks and gluons? You might hope that this is a perturbative process. You might hope that we can start with the 3 valence quarks, and because QCD allows interactions between quarks and gluons, we exchange a gluon. If you can exchange 1 gluon, you can exchange 2 gluons. If you can exchange 2 gluons, you can also emit a QQ bar pair and loops of gluons. Unfortunately, or fortunately, we know that the coupling in QCD is not a constant. It actually changes with energy. So at very high energies, where it's small, one could actually do a perturbative calculation and truncate this series of Feynman diagrams and get a reasonable prediction. But where the proton lives is not where the QCD coupling is small. Instead, the QCD coupling is larger than 1, non-perturbative, and one would have to sum all of the Feynman diagrams in order to get a prediction. So let me talk about ways that we do make predictions from QCD now, and that includes lattice field theories and effective field theories. And we'll see critically that because of the difficulties and the broad reach of QCD, we actually need to combine both of them to get some of these estimates that we're looking for. As you just heard, Feynman was an advocate of computers very early on. He realized that if an analytic solution is elusive, then you try to solve it numerically. And what's great about this is that the path integral formulation is almost uniquely qualified to shine in a lattice formulation, as we'll see. And it's also a place where regularization or normalization is particularly clear. So what is lattice field theory? It's a numerical procedure for calculating a path integral using Kris Munroe's language, it's a simulation. It's a simulation of QCD. And the way this works is to discretize space-time, the same way if you were trying to do a continuous integral, you could approximate it through chunks of the integral that you sum up in a discrete way. Here, we break time into segments, we break space into segments, and the simplest case to envision is one where you're talking about just a simple quantum mechanical particle. And what is happening here is that you want to get the probability amplitude for a particle to start at a space-time point and end at a space-time point. And what Feynman knew is that the way you obtain that probability is to sum up all possible paths. So it's an integral that's been discretized. And this path is weighted by a probability amplitude. And that's the action in the phase and the action that depends on the Lagrangian. Ultimately, for us, the Lagrangian of QCD. Of course, there's a technical issue where you don't actually want to be putting this phase on the lattice, and instead one rotates to Euclidean time so that the numerical calculation becomes feasible. So that was an example of what happens if you're talking about a quantum mechanical particle. But of course, we want to do a field theory. For a bosonic field theory, you can think once again of time being discretized, and now you're taking all possible field configurations in order to sum up all probability amplitudes to get an actual prediction or lattice measurement. And focusing in on what just one time slice for the moment, if you sum up and down over all possible field configurations, then this is the kind of motion that you'd be looking at. However, what we really want is a fermionic field theory, not just a bosonic field theory. I have on the left here what a totally separate path would look like. Ultimately, with fermions, we also need to deal with quark loops. Here you see essentially what is a lattice field configuration or a gauge configuration, where you've got a particle on each site and the loops are closed fermion loops. What this is doing is simulating summing all the Feynman diagrams, and it's doing it in a non-perturbative way, which is just exactly what we need in order to deal with these low-energy processes, such as how it is that protons are bound from quarks and gluons. The other thing that is so nice about lattice field theory is that the regularization is easily visualized. So you see here that as the strong coupling constant changes with energy, this is a change that echoes what a lot of the parameters in QCD do. They change with energy. And this can be regularized and understood using the space-time lattice spacing. So as this spacing changes, you are able to essentially probe shorter and shorter distances as A gets smaller. And that I wanted to indicate by where you can reach on the strong coupling constant graph versus energy. But this is not sufficient. And that's because it's great to try to do a simulation and put all of physics in a box, but unfortunately, there are so many distance scales involved in what we want to learn that it's difficult to put all of this in a box and simulate it at the same time. We've already seen a little bit about what kind of computing power is necessary to do even a fairly straightforward calculation, and these are not only very complicated because of the non-perturbative issue of QCD, but also because of the separation of scales. So suppose that you wanted to study a high-energy collision. Let's suppose you wanted to look for beyond the standard model physics. What you do is to collide protons, and if something interesting is happening, that means that it's quarks and gluons that are collided. This is in the realm of perturbative QCD. You can expand in alpha S to look for this new physics, but in order to actually detect it, you have to go through the process of hadronization and unpack from what you found in your detectors what might have been happening after you've gone through this non-perturbative process back to the actual high-energy collision that gave you the initial, say, new particle that you were looking for. And so what we do is take advantage of the distance, the different scales, the high scale versus the low scale, and an effective field theory is actually going to let us expand in those two scales. So I can't put them all on a lattice, but I can actually utilize the different scales. Going in the other direction, we want to be able to get to heavy nuclei, and you can see the disparate length scales involved here, where you're starting with short distance quarks and gluons, making a proton, and then many orders of magnitude larger, trying to get that EFT. So, lattice field theory has this problem of separation of scales, but fortunately, effective field theories actually use this separation of scales as a feature. We can do this because a ratio of scales gives us something too small to expand it, and we can do perturbation theory. It's critical, however, that in order, even now, though in the EFT we're now in hadron degrees of freedom, before we can actually make the connection between non-perturbative quark-gluon languages and the hadrons, we have to impose the symmetries of QCD on that language. So one example of the concept of effective field theories is actually something that Feynman worked on back when it was experimentally noticed that parity is not conserved in all interactions. And what he saw and what he modeled was essentially an effective theory where he was attempting to encode this vector minus axial vector structure. There was some coefficient that you could map onto what was then unknown physics. So the degrees of freedom here were actually the nuclei that were decaying, but also the protons and neutrons taking place in this participating in this parity-violating interaction, and then the leptons going out as well. And now we know that what's actually happening is that underlying this V minus A structure is actually weak interactions and the exchange of a very heavy weak boson. So the idea behind utilizing the separation of scales here is that you can condense, or in the parlance, integrate out these very heavy degrees of freedom and encode the necessary physics, the important degrees of freedom into an effective theory. And that's what we now understand weak interactions to do. So let me say a little bit about creating an effective field theory. Again, it depends on the separation of scales. And on the left-hand side here, I've got again, echoing how it is that a W boson can be integrated out of a theory and produce a contact interaction that's part of the effective theory. And what you do is either start from unknown physics or start from the standard model, and you have your degrees of freedom that include the top, the Z, the W, all of the dynamical particles. But if I'm interested in what happens in my detector, what it is that I'm measuring, the hadrons I'm measuring, what I do is match that high energy theory onto an effective theory where the top quark is gone dynamically, but its physics is encoded in the lower energy theory, in the coefficients of the lower energy theory. The running here is meant to specify QCD renormalization. I'm going from a high energy scale where alpha is small down to a low energy scale as alpha gets larger. And I can continue that in stages, but eventually I hit the point where I can no longer perturb an alpha S, and that's where the breakdown happens. That's where I have to go from a quark basis to a hadron basis, and that's where I need to include the symmetries of QCD. Some of these approximate symmetries are chiral perturbation theory, where I take the limit where the light quark masses, the up, down, and strange, are looked at as an expansion about 0, and where the heavier quarks, the charm and the bottom, the top doesn't hadronize, are encoded into what's called heavy quark effective theory, where we take the limit where those heavy quark masses goes to infinity and we perturb about that. So it's all a matter of looking for ratios that one can do perturbation theory in order to complement what's happening on the lattice. And the other example of an approximate symmetry is taking the number of quark colors to large, and then you can expand in 1 over the number of quark colors. So this is the method. The method is that you start with lattice QCD, this path integral formulation, this simulation, and that is used to calculate the short distance physics, which then is encoded in a coefficient. The symmetries of QCD and this perturbative expansion allow you to create an effective field theory which has the physical degrees of freedom, the hadronic degrees of freedom, and putting those together, one hopes to get from QCD to the physics that is much more complicated, but hopefully we can understand in terms of the underlying QCD. One example I want to highlight is where the coefficients of what's called pionless EFT, so this doesn't mean that the physics of the pion is gone, it just means that the pion is not dynamical at these energies, and we encode its impact into a coefficient that's calculated from the lattice. And that is written again in terms of hadronic degrees of freedom. And what these collaborators were able to do was to go all the way from the QCD non-perturbative quark gluon language all the way up to showing that in fact helium-4, oxygen-16, calcium-40, all of these bind, and you can see kind of an alpha cluster effect. I also want to point out that this is not actually obvious. The leading order effective field theory excuse me, did not give rise to binding in oxygen and calcium. One had to go to the next to leading order, which is why it's so important that a perturbation theory works in effective field theories, and that is order by order improvable. I also want to highlight another example of this type of analysis that's happening in H06 later in this conference. Kind of looking at it from another point of view, this is another example I want to talk about, because here, the Milk collaboration calculated the simulated QCD on a lattice and then matched that to the heavy quark effective theory for mesonic, heavy meson propagators, and then matched that to what was measured in an experiment for the hadron masses in order to pull out some fundamental parameters of QCD. And those parameters are the quark masses. And I want to emphasize again how those quark masses actually do change with energy. The mass changes depending on at what energy you ask the question, what is the mass, which is why you've got explicitly this 2 GeV dependence here. Finally, the last one I'll highlight is one that echoes Feynman's V minus A theory. So here we have a weak interaction, the V minus A interaction, only now instead of just looking at the protons and neutrons, these are living in a nucleus. And this is something that was possible again by using pionless effective field theory. And what's so interesting about this is that because this tritium beta decay is so well measured, it means that you can compare that measurement to the lattice EFT calculation that includes only standard model physics and look for a discrepancy, and that's how you can look for possible new physics. And I want to highlight other examples of few nucleon physics using this technique, again, so that you can look at some of these talks later in the conference. So, Feynman's impact. Feels a little awkward to try to put it all in one slide, but I hope that I have convinced you that what started out as his parton description, we have built on that effective theory, actually, in order to understand how quarks and gluons in QCD actually behave. His path integral formulation completely changed the way we visualize field theories and allows us to do QCD on supercomputers. His path from regularizing QED, all of those tools and techniques were completely critical in being able to regularize QCD and obtain that scaling of this QCD coupling constant with energy that I showed. And of course, Feynman diagrams are completely, excuse me, ubiquitous. I want to end with Feynman's scientific method. One of the reasons that Feynman was inspirational to so many students of science is because he encouraged us to think for ourselves. Doing physics like Feynman means finding joy in the process. Following his lead, we can be curious about everything. When I see a tree being taken down in a neighbor's yard, I have the opportunity to watch how a crane works, understand the forces involved. When my power outlet stops to work, I got to find out that there's something called a ground fault interrupter. And now I know how it works, and now I know how to replace it. This is, again, how critical curiosity is. If my explanation of spin-orbit coupling is being misunderstood by my student, this is an opportunity for me to learn how to be a more effective teacher for that student. Feynman acknowledged that there was a lot he personally didn't understand, and there's a lot nobody understands. And that just because something has always been done that way doesn't mean it's correct. Challenging existing ideas is critically important to scientific discovery. If your experiment is giving you data that does not agree with the prevailing theory, go with the data. If your theory is giving you something that disagrees with the data, go with a theory, because in the end, when data and theory don't agree, this is an opportunity to understand something nobody has understood before. Feynman liked to quote his first wise advice to stop caring what other people think. That is not a license to be mean to people, but really another way to practice integrity. To paraphrase him, if there are 50 people working in lockstep on one thing, then your best chance of a discovery is to look someplace else for solutions. Many of the behaviors that Feynman demonstrated and recommended for physics discovery are now articulated in what Carol Dweck calls the growth mindset. This is the idea that students learn most effectively when they do not come with prejudices about their own, quote, pre-existing, unquote, abilities. When they realize that they can develop techniques and skills by studying and practicing, when they do not fear challenges and confusion, but embrace them as a chance to learn. Look at research by Aguilar Walton and Carl Wyman, who are applying these concepts in their physics education research. Finally, let me ask the following. The best science is done when scientists are free to think about science in a community that respects and values them. One thing that Feynman did for science was to make character and personality an integral part of how learning and research is accomplished. He shared his joy and excitement about science. Our physics community has not always chosen to share that joy and excitement with people who don't look like Feynman. And that is tragic, because that means we lose people who can contribute and who want to contribute. But the way forward is very clear and requires applying Feynman's scientific method very broadly, not making assumptions about who can't be a scientist, but enabling every student and every colleague to be the best scientist they can be. That means embracing whatever makes a scientist unique. That means attracting people to our field who have the widest possible range of experiences and perspectives. To paraphrase Michael Miller from DNP 2017, Physicists in the Wild, there is just no downside to inspiring and supporting every student at the earliest possible stage of their career. We can all become better mentors by applying Feynman's scientific methods to ourselves. We can think about how what we do or say impacts others. We can experiment with ourselves by asking, if the student in front of me were a different color or a different gender, would I be acting differently? If so, is it helpful or not to bringing out the best in that student? Anything you can do to help a student use more of their intellectual power towards research rather than trying to potentially navigate a hostile environment yields more discovery. Does it take some of our own intellectual power to do this? Yes, it does. But it is part of our responsibility as stewards of physics, and this can be our legacy. I want to also ask you to consider going to some of these panels and roundtables so that you can see and get some tips on how to do that. I also recommend reading Belonging by my colleague Arlie Petters, and I want to thank my colleagues for their help in asking the right questions so that I could create this talk.
key question is the boundary between quantum mechanics and classical physics. Do you expect that boundary to be defined soon, and why or why not?
Do I expect the boundary to be defined how?
Some physicists
soon.
say quantum mechanics is applicable to universe. I don't
Quantum
think
mechanics is
quantum
an integral
mechanics
part.
is
Quantum mecha-
applicable to an atom or a proton. The boundary between classical physics and quantum mechanics has to be defined. Do you expect that boundary to be defined soon?
So I don't think of it as being a boundary at all. So much of our life is actually driven by quantum mechanics. When you look at the path integral formulation and look at the phases that interfere constructively, you're going to get a classical limit. But quantum mechanics is everywhere. We don't always measure it, but it's everywhere.
Hi, I would like to make a comment on your saying that he questioned authority. He did more than question authority. He ignored authority.
I like it. Thank you.
Both levels, here and one above, and so I point you to that. If you come down very quickly, you could probably grab one of our speakers for a question or two. But otherwise, I'm going to release you all for coffee. And thank you again. Thanks to the Kavli Foundation. Thanks to our speakers.